Hello everyone, welcome back to ECE410 Power Electronics, class number 8. Today we're going to talk about the converter design. That what this means that we're going to give you some specification of the converter. You have to come up with the design. That means you're choosing the L values and C values depending on the specification. So let's move with the one buck converter design. So for the buck converter design, we're planning to choose L or C values over here depending on the specification. So what is specification we have? We have the input voltage and output voltage, 24 volts and 5 volts over here. And this is a 100 kilohertz. That means your T time over here, period, is 1 over F is 1 over 100 kilohertz, should give you 10 microseconds. Your T is 10 microseconds. Then the power delivering is 25 watts. Then ripple of the current, inductor current, should be peak to peak 1% or less. So with that, now we know the equation here. V out is dV in. With that, your DT ratio is 0.208. Then your output current, you're delivering 25 watt at 5 volts. Your output current is 5 amps. And when switch 1 is on, if you look at here, switch 1 is on, right? You are connected to input to output. So VL is basically V in minus V out. That is 19 volts. All right. Now, if you try to calculate the L value for this given things over here, again is 10 microsecond for the time. So switch 1 is on. We're doing only switch 1 is on for now. VL is 19 volts. You have seen that in the last slide. So VL L di dt, and I can also convert the di dt, delta I, delta t, and we're looking for L, right? We know VL, which is 19 volts, delta t is dt over here, that is 2.08 microseconds, and delta I is 1% of the inductor current. Inductor current is 5 amps because your inductor current over here is average inductor current is equal to average output current. So output current is 5 amps, so inductor current is 5 amps for this particular converter, okay? So that is your delta I is 0.05 amps. So your delta I needs to be less than that, right? That's what we said. So your L should be higher than this equation over here. So if you put everything values here, 19 volts, 2.08 microseconds, over 0.05 amps, you get L value is 0.792 millihenry. All right. So that is what we did for the switch 1 is on. I want you to do when switch 1 is off. It should come up with the same values, but with the different parameters. All right. Check that. So now, remember that we got L equal to 0.792 millihenry or higher. So we're going to choose 0.8 millihenry for designs that should get the current ripple less than 1%. So now, if you have a 8 microhenry inductor, what will happen? If you do the same math over here, everything is same. Your L is 8 microhenry. Your peak-to-peak ripple becomes 5 amps. It's basically 5 amps because of the sum. Decimal point is 5 amps. That's what it means. So that means you go lower with the inductor value, your ripple goes up at the same proportion. So remember here, 0.8 milliamps and 8 microhenry is 100, 100 times difference here, right? 100 times difference here, right? So look at here. Your current ripple should be 100 times too. So so your current ripple was 0.05 amps. Now it went to 5 amps. That means you make it 100 times bigger because your inductor is 100 times smaller, right? So how does it look like? If we do the draw here, so this is the 5 amps inductor current, IL, right? So you have 5 amps peak-to-peak ripple. That means your ripple over here and here is 5 amps. So if you go from here to here, the peak-to-peak ripples is your 5 amps. That is your delta IL. All right. So smaller the inductor values, bigger the ripples, and goes by the same proportion. All right. So now let's draw what we have. So now we had that. Let me get a different color here. Let me get this color. Okay, now, so when switch 1 is on, this is the switch 1 is on, right? Almost 20% time. and this is the switch 2 on, what is almost 80% of the time. When switch 1 is on, your VL is 19 volts. When switch 2 is on, 1 is off, is minus negative 5 volt. That's the VL here. IL is 5 amps is average value, and it has 0.1% peak-to-peak ripples. So that means half goes ripple here and half here. So it varies from 4.975 amps to 5.025 amps, and average is 5 amps. Then your input current, if you look at the circuit over here, input current here, I in, only connected when switch 1 is on. So that's why your input current only part of the inductor current when switch 1 is on. And your IC, look at here, IC. When switch 1 is on, your IL coming in, and there's 2 branches here, right? So your output current is 5 amps, right? And average IL is also 5 amps. So only the ripple goes into the capacitor for this particular converter. And when switch 1 is off, 2 is on, this is IL is circulating here. As IL is circulating here, right? So that means it's still the same thing. So IL equal to I out average value, and also ripple goes back. Ripple goes back into the capacitor in what do you call it, in opposite ways. So in that case, so your ripple, only the ripple of the inductor current is your capacitor current. So IC is the ripple of the inductor current. All right. And output is 5 volts for now, because we didn't design the capacitor yet. We're going to design the capacitor and come back and do the output voltage. So for now, we have the average output voltage is 5 volts for here. And I also mentioned one thing over here. Input energy should be the output energy. So input energy only happen when switch 1 is on. So V in, I in time dt. And output energy should be always constant, and the output supplying constantly output. So output voltage, output current times T. So T will be cancelled over here, right? Then we have D is 5 over 25, which is the D, and 5 volts, 5 amps, and T. TD cancels. Then if you look at both sides, it should be 25 equal to 25. That means energy also balanced between input and output during the switching. So now let's do a capacitive filter design. How to design a capacitor for this converter, which is a buck converter. So now, if you have PWM switching on and off, on, this is the on here, this is off here, and so on. So as you saw that in the last slide, that your capacitor current is basically a ripple of the inductor current. So the ripple is right here. I draw them here. So ripple when it's on is goes up, and when it's down is goes down, and so on. So this one here, for this particular one period, right, from here to here, T, this is your half T, right? So it's got half of the on, half of the off, so this will be half T. So at this time where your capacitor is charging, at this time is your capacitor charging and your current increasing, and so on, right? So your IC is C dV dt. If I try to find voltage, is 1 over C integration IC dt. So now if I integrate for this half of the time over here, T over 2, that's what happened. So now if I go back here, your capacitor has initial voltage and final voltage, initial voltage. That is your peak to peak voltage here now. So what is that? Means your capacitor has the initial voltage and final voltage. If you subtract each other, that's your voltage, which is peak to peak. So now if I try to integrate that current IC over here, I can integrate for that particular half of the time, and I'll get the difference between 2 voltage peak, right? So if I do that, over here, if I integrate that, it would be that particular triangle. If I come over here, the particular triangle right here is half, base is half T, and also your height is delta IL over 2. So they're basically the area of the triangle. So that will be a half T, half IL over 2. So that is the integration right here, right? That's the integration right here. Then 1 over C, that integration will give you the peak-to-peak capacitor voltage. That is right here. You can do this, or you can come back this one here, and the fundamental equation for capacitor, V equal to Q over C. That's the capacitor equation, right? So delta V equal to delta Q over C. The C is not changing, only energy storing is changing. So delta V is 1 over C here. So this guy over here, how much energy stored? If I go back here, so if I go back here, if I take this, let's take another color. I'm getting out of color here. So if I take this particular one here, so how much energy is stored into the capacitor depends on time and current of this, right? So that's basically area of the triangle. So it's half T over 2 over half delta IL. So if I look up back here, so half T over 2 delta IL over 2, then also give the same equation here. So this is the same equation. So that means peak to peak ripple voltage is basically T over HC delta IL, right? This is for buck converter. So if I use the equation for our design here, our design is, I'm looking for delta V, right? We have T is 10 microseconds and HC over here. And my current, inductor current, peak-to-peak ripple is 0.05 amps. So trying to find C, C should be greater than or equal to these values over here. So if I put all the values back here, I will get 1.25 microfarad. So that's the capacitor. So now with the capacitor, if I go back to my drawing over here, so now my peak-to-peak is 1%. So that means it's gonna go something like that. So over here I'll get 5.025 volts. Over here I'm gonna get 975 volts. So that's the completes all my waveforms. So with that, we know how to design a buck converter now. In the class, we're gonna do how to design a boost converter, and also so many more comes after this. So look at the circuits, look at the design. How do we apply the equation to design is very similar, a little bit different with the circuit to circuit, but fundamentals very similar. Look at them, and if you have any question, come back to class with your particular question and notes. I'll see you in the class.